Welcome, class, to Energy Plant Best Practices. Thank you for coming today. Really appreciate you making the effort on a cold day. And like I was telling Tom, the last time I've been down there where we parked was I was riding my bike right through there. I was actually riding my bike from DC to Pittsburgh. So anyway, what we're going to be talking about today, my name's Matt Tyson, engineer with Johnson Controls. Been in this area for 4 years and been in the Mid-Atlantic area working on buildings and HVAC systems, mechanical, design build, central plants, boilers, chillers for 25 years now. So it's kind of crazy to be able to say that, but I got out of Geneva College in 1987. I don't know why they let me out, but they gave me a paper and said I supposedly took the classes and passed. Anyway, so what I want to talk about today is building efficiency best practices, central plant, and heating, ventilating, and air conditioning. And we want to accomplish two things today. Big picture, what we want to talk about is how you approach energy efficiency, the methodology, the mindset, the rules of the game. And then what we're going to do is also learn about chill water and cooling systems, HVAC systems, as the subject matter. So don't get too caught up in the technical aspects of the subject matter if they don't all apply, for example, to your world. Still think about the guiding principles that we're learning. So if you take nothing away from today, I'm hoping that you take away some of the points on how you approach energy efficiency in total. If you take away some interesting factoids about chillers and VAV boxes and controls, that's great too. So Janelle, it's fine if people ask questions and have input as well?
Yeah, absolutely.
So please raise your hand or just blurt out something anytime we're talking. Make sure this is applicable to you. If you have a question, don't wait and ask it later. Just ask. Okay, so here we go. Energy Reduction 101. So when you're approaching a new facility, I know there's net zero buildings, there's green, there's everything, there's ASHRAE, there's all kind of guidelines and there's all kind of methodologies out there. But for me, my job is to go out there, meet a customer, and help them save money by reducing energy, by reducing CO2 emissions, by being more efficient, by having the operations and everything work better. So I'm always in this position. So what do? I ask about 6 questions in my mind, try to guide the process according to these principles. This is kind of something that I just kind of came up with. Probably stole some of it from somewhere along the way, but the bottom line is this is how I think. Okay, number 1, should the equipment or system be turned on or off? Maybe we can just turn it off. Okay? That's simple. Demand controls, demand response. Maybe it's Friday afternoon, it's 3 o'clock, buildings like this building has a lot of brick, and it's got all kind of inertia, and it's kind of got a flywheel effect, and you just turn it off. Okay, maybe there's ventilation requirements, but maybe we can turn things on and off. That should be number 1 question, because before you start spending a ton of money on retrofits and complicated equipment and complicated systems, that you should really start thinking about what in this building, what in this system can simply be just turned off or managed better. It's number 1 question. How could we reduce energy? How can we reduce energy costs? How can we make the operation more efficient? Just through a better control strategy. Before we do anything to this piece of equipment or system, maybe we can control it better. Maybe we can have demand response. Maybe we can have optimum start, stop. Maybe we can do reset control. Maybe we can make the system respond more closely to the load. Who knows whether, if you're sizing an air conditioning system, which would be worse? Would it be worse to size the equipment too small, or would it be worse to size the equipment too large? What do you think? Too small or too large? Which one would be worse? Come on in. Overall negatives, overall problems, overall inefficiencies, so on and so forth.
If it's too big,
Too small might cause a political problem like 1 week of the year in July when it's really, really hot. Too large could cause energy efficiency problems the entire year, could cause cycling, and cause the equipment to age too quickly. It could have humidity control problems. Unfortunately, a lot of times equipment is sized too large. So maybe we can use controls to make it be smaller and make it respond, variable speed drives. Maybe we can alter the system that was too large. Now, a lot of times it isn't the engineer and architect's fault because people have done lighting retrofits. They've done window retrofits. The computers keep giving off less and less heat. So over time, the equipment maybe sized 10 years ago for something, it's not there anymore. That load isn't just, it's just not there. So controls. Can the operation itself be optimized? Can the way you do business, can whatever's going on in that building change? Can you possibly alter the operation in order to save energy? Okay, so I just asked 3 questions that sold nothing for Matt and Johnson Controls. All it did was try to do better with what you had. It's not until you get down to number 4 where you're actually starting to put equipment and things, devices into the equation. Retrofits and upgrade. Okay, you've gone through the discipline of checking those first 3 things. Now you earn the right as an engineer, energy engineer, to start recommending variable speed drives, two-way valves, more efficient controls, okay, DDC, direct digital control systems, all these things that cost money, but you've been through the discipline of the first 3. Number 5, a lot of times we're looking for heat recovery. If all the other things are true and they're settled and you've got it all figured out and you know the loads, look for heat that you could recover. You could use that heat for heating. You could use that heat to drive cooling. You could use that heat to make electricity. And number 6, you've been through it all. Maybe we do need to replace this system. Okay? But that's only after all of that other work. So, chillers. It's the example. Let's use this practice that we just learned on a chiller. Okay? First of all, chillers. Should the equipment be turned on or turned off? I got 2 or 3 chillers. Which one should be on? Which one should be off? Should all 3 be on? Should 2 of them be on? Should I be running chillers? First thing you need to learn, first thing you need to understand when you're looking at that, and again, I was talking to Tom about, in the world of chilled water, chillers and central plant systems, chilled water is what you're looking at. But if you have packaged rooftop units, same thing applies. So instead of chilled water, you'll be looking at supply air, the temperature of the air, and things. All of these principles, these BTUs, these flows, all have a corollary in the packaged equipment world. So it's really just, this is the example, but principles are guiding. Okay, what is the proper evaporator flow of a chiller? What is the evaporator flow? Does anybody know? That's just chilled water. The chilled water goes through the evaporator. Condenser or cooling tower water goes through the condenser. All right, so you have the evaporator, that's the chiller barrel. You have the condenser, that's the cooling tower barrel. So what is the proper evaporator flow for a chiller? Okay? At 10 degrees delta, if I'm coming in at 55 degrees chilled water, which is typical, and I'm coming out of my chiller at 45, okay, that's a 10-degree delta T. So if you do the math, simple equation, it's 2.4 gallons per minute per ton. Okay, so why does that matter? Well, if you have consistently a delta T of 5, you're only half loaded. And you can start to wonder, why am I running that chiller? What if I have a couple chillers all half loaded? Maybe I should change something so that I'm only running one fully loaded. Remember how we talked about it's inefficient if it's only partially loaded? So you're doing retro commissioning in a building. You're doing commissioning in a building. You're looking at cooling equipment and load. You're trying to match that cooling equipment to load. So these principles start to make some sense. So first thing to do is understand that. Okay, this is, some of the slides that you'll see in here are my synopsis of like real life stories that happened during my life as an engineer. Just tried to show like what happened. We're not going to get too caught up in this kind of stuff, but the bottom line just shows a real-life example of what we're talking about. So, what happened? Does this thing do a pointer or no? Okay. Right in this time frame, evaporator flow reduced because of added air handling unit load. The building was expanded, they put more air handling units in, so evaporator flow is reduced through the chiller because of increased resistance to flow. Okay? Because that corresponded to the added air handling units. Okay? What did they do? They added a water pump to maintain water flow. Okay? So we lowered the flow because of air handling units. We added a pump. And what did we need to do? We need to balance the system. We need to make sure that everything, the air handling units and the chillers, all had proper flow through it. Understanding the load, understanding the chiller, understanding the pumping was the result of just making sure that things were being done right. Okay, excessive load. Starting in 9/17, leaving chill water temperature above 40 degrees. High flow, excessive load. The analysis, the system load periodically was higher than full load capacity of 2 chillers. Just had a short period of time where 2 chillers weren't good enough. Actions need to have the water system balanced to see if conditions improve with proper air handling unit water flow. Resolution, running, it's open in this case. Running 3 chillers during periodic load to maintain needed chill water temperature. Okay? The impact is running 3 chillers at the same time reduces condenser flow, can lead to compressor stall and possible surge. 3 chillers running at reduced load, less efficient than running 2 chillers fully loaded. So this whole graph, this whole slide shows a situation where an owner added some air handling units, noticed the impact, and then instead of running 2 chillers, which they had been for many years, just added the 3rd chiller during the time that the load started to go down. Very inefficient. The demand went way up. There's a spike all of a sudden, a couple hundred kW. All of this was just an immediate response. We're coming in as energy engineers. We're saying, look, if we can keep those 2 chillers running, we're going to save energy. We're going to reduce wear and tear on the chillers. We're going to make sure we don't get the demand spike. Okay, what do we have to do? We're going to have to go through all the air handling units, all the pumps, all the chillers, make sure the flow is right, make sure no flow is where it shouldn't be, balance the system, so we can ride through these peaks with only 2 chillers. So it's getting back to that, is it on, is it off? Make sure it's on. If it's on, maybe it doesn't need to be. Ultimately, when we did get through there, we had some flow going to air handlers that didn't need to be. We had flow going to places that there weren't even anything there. So once we managed the flow through that building, we got it back down to 2 chillers and everything was fine. Make sense? That is really, really simple, but believe it or not, those are the kind of things you find out there in buildings. So, what's proper condenser flow for a chiller? Is there such a thing as cold, yes or no? Is there such a thing as cold? Is there such a thing physically in this universe as cold? Yes or no? Is it measurable? Yeah, you're shaking your head. The answer is no. Okay, there's such a thing as heat, BTUs. Okay, what is cold? Cold is the loss of heat. Cold is a removal of heat. I mean, what does air conditioning do? It works during the summertime, right? But it's about heat, not about, quote, cold. It's about taking heat from one place and moving it to another, right? Heat transfer. So what does a cooling system do? It takes heat from the space, puts it in the air handling unit, uses the chill water to take that heat to the chiller. The chiller uses its refrigeration cycle to take the heat from the chill water to the condenser water. The condenser water takes the heat from the chiller to the cooling towers. Okay, rooftop unit, air, refrigerant, R22, R123, whatever, to the fans on top of the rooftop unit. Those are condenser fans. Same exact thing going on. With a chilled water system, it's just another heat transfer medium, which is chilled water and condenser water, because it's bigger. Regular air handling units, rooftop units use a phase change for the heat rejection. Don't use a phase change for the heat rejection. They just reject heat from the refrigeration cycle right to a radiator coil on top of the rooftop. They do that in a sensible fashion. In other words, they just take heat from the refrigerant and just blow air over it out the roof and take the heat out of it. Real simple. Larger systems using cooling towers are using a phase change, evaporation. The cooling tower uses the principle of evaporation. So for a box that's only 2 or 3 times the size of a condensing unit, it's 10 to 20 times the heat rejection because it has that phase change in it. Does anybody know what I'm talking about? Yeah. 1,000 BTUs per pound versus 1 BTU per pound. Okay. Sensible is just chugging along 1 BTU per degree per pound slowly. As soon as you hit that phase change from liquid to gas, boom, the heat comes out really fast. So the condenser water is the heat rejection side of the chiller. What are we looking for? We're looking for 3 gallons per minute per ton at 10 degrees. Another thing, okay, sequencing chillers, problem definition, how to take advantage of lower entering condenser water temperature. Looking at the data on the chiller, majority of the year you can leverage ambient under typical design temperature of 85. Mechanical engineers designing a system for the worst case, putting in the chiller and the cooling tower for the July, August, and basically setting everything up at 85-degree condenser water temperature. That's where the sweet spot is for the design. However, during March, during April in Pittsburgh, May, September, October, November, there's plenty of time you can make colder water than 85. Well, what happens when the chiller sees water colder than 85? Well, it's like it has like a big sigh of relief. All of a sudden, all the refrigerant temperatures and pressures go down. The energy required to do its job goes down. Okay? Now, you don't want to set it up like that permanently, because during July and August, you can't make colder than 85-degree condenser water. It's hot out. It's 90 degrees outside. So you got to go back to the design. But basically what we're saying is, hey, it's possible without changing a thing, just to kind of look at, well, wait, let's let the tower rip away and make as cold of a condenser water temperature as it possibly can all year long, modify the controls a little bit on the chiller to accept that condenser water, and all of a sudden its efficiency gets really good. Okay? Simple trick. You didn't even do anything. You didn't spend a dime. It's just understanding the principle of refrigeration. It's amazing how many building owners still don't understand that. Okay? But it makes common sense. All right? So in this case, we found hours that we could take advantage of it. We presented it to management. This is Johnson & Johnson, by the way. We ended up doing it. The savings was $30,000 to $40,000 a year on one 1,200-ton system. Didn't cost anything. Okay? It's just an efficient way to use what you already had. So we haven't done any retrofits yet. Could we improve the operation for control strategy with a control strategy? Okay. Again, we're talking about chillers. We can talk about any HVAC system here. This is really, really simple. Startup peak demand management. Plant demand was peaking on Sunday night. Start up by turning on several machines simultaneously. The startup peaks exceed operational peaks. Single peak established charge for the next month. New procedure was written to stagger start the equipment, eliminating the excess peak demand. Sounds obvious, right? Still today, find many, many places where you just start asking questions about how they run their business, how they turn things on, how things happen. Oh, well, we pretty much start the entire plant on Monday morning at 8 o'clock. Well, if you could just start it up at 1/3 at 8, 1/3 at 9, the other third at 10, you wouldn't spike to 1,200 kW. You'd only go up to 800 kW, 400 kW. When that gets set, that's the entire month's demand for decaying light. So These are really, really simple procedures, but they're there for the taking if you just start understanding what's going on. What we're talking about is the response of the chill water system, basically, in this case, but it could be any system. Air handling unit. Okay, the chill water system is serving air handling units all over the place. Okay, and this goes back to the argument, that example a couple notches before where they found that, oh, they added an air handling unit and then it made them have to bring on 3 chillers. This is going back to that same example of just look at your entire building, make sure you're not turning on air handling units just because you are, even though there's nobody in there. This school example, I mean, yeah, an auditorium, nobody's even, like, they might have this little one thing in there, but then the hours go by, there's not even anybody in there until like 3 o'clock when it's time for choir practice, yet they driving that air handling unit down the entire time. You know, gymnasiums, the shop area, the locker rooms, just looking at your schedule of all your air handling units throughout the building, making sure it makes sense, because anything that's excessive there, just, well, we want to make sure that it's, you know, completely conditioned, because in case somebody walks in there, could be paying you a huge price back at your chiller. Again, go back to the example of rooftop units, same thing applies. So, temperature setback. Still today, and this again goes to schools, still today when we go into many schools, there's no actual time clock. It's just manual in each school. Still today, I was in, I'm not going to say the names, but I was in 2 different school districts last week, and I was mind-boggled that 2 or 3 elementary schools and a high school and a middle school, manuals, the whole thing manual. I mean, in 2014, you still can't think. So that's out there. People need help putting in simple computer-controlled time clocks. They can schedule their facilities. Again, that has a huge impact on the central plant cooling system. Any questions?
So my question would be, do you think that the reason behind that is because of depreciation value of the system, the accelerated depreciation value of the system, and you pay back at 30 years or whatever the period is? So they're not doing anything until they have to.
I'm not sure. Yeah, I'm not sure, like you're sort of like waiting for a big retrofit. But in these same schools, they had done lighting retrofits and window retrofits. There have been energy reduction going on. I sometimes think that, like, we in the energy reducing community, like I'm in the, you know, I'm CEM, I'm part of the AE, we're sort of to blame because we go around doing the low-hanging fruit that's easy to understand and that gets you an immediate result, and don't delve into these boiler controls and chiller controls and HVAC controls as much, because it is maybe perceived as too long of a payback or too complicated. It just sort of gets brushed over. So I don't know. Yeah.
What's the rule of thumb for, you know, to reset that for 8 hours or 12 hours in terms of, is there a rule of thumb at all?
I don't really know of any rule of thumb, but I mean, from my experience, if you take a bunch of buildings, whatever you want to say, and energy efficient, you take their BTU per square foot per year, and you start looking at the buildings, and you understand what's going on, you bring them into control. I mean, I've seen the energy drop probably between 5 and 10%. Like, it didn't have any setback, and now it does. That's where I normally see it. How often do I'm dealing mostly in existing buildings that have been probably 10 to 15 to 20 years since their building was designed and installed. So I'm not dealing in new buildings. So the answer to your question is every time. She asked, how often do you see the energy model and the operation of the building different from the original design and intention? But again, if I'm dealing in new buildings, it'd be different. But for me, there's been drastic changes. They've moved things around. They've done things to the lighting. They've done things to the way they operate the building. Equipment has changed. They've handled it in one way or another, or retrofitted in one way or another. So. Okay. Everybody knows about ASHRAE 62, right? In this building right here, how many CFM of outside air? How do you say fresh air? Outside air. You don't know exactly if it's fresh or not. How many CFM per minute, how many cubic feet per minute of outside air do we need for each of us in this room right now? You're close. You're closer. 15 is schools, but for an office building, 20. 20. Now, the person who said 10 is actually right, because in conference rooms, you're allowed to get away with the fact that it's not constantly occupied. So for rooms that are typically a 2-hour occupancy, you can get away with 10, but you have to have an engineering report explaining why you're doing that. Out there in the cubicle land, it's got to be 20 per person, okay? Schools is 15, and there's all kind of different numbers. Bottom line is 20 CFM of outside air per person for a typical office building. However, when let's say this facility right here is occupied from 8 a.m. to 5 p.m., do you think every space that might have a person that an engineer has painstakingly designed the VAV boxes and the outside air system to get 20 CFM per person to that spot? Do you think they're always there? Right.
But the number of persons computed by square feet per person.
Right.
Not by number of workstations.
Right.
But that can add to receive the
Yeah, Tom brings up a good point. Not only the occupancy change, but where the occupancy is based on the just generic design principles. So what we're doing these days, and this is I'm not giving you something that's cutting edge. This has sort of been around a little bit. I'm sure, Tom, you see this in your new designs now with some of the mechanical engineers out there now that are doing a good job. What we call demand-controlled ventilation. So the CO2, CO2 is not a contaminant. CO2, ASHRAE is saying, what, 700 parts per million above ambient is acceptable in a building. The CO2 in a submarine is, 10,000 parts per million. It doesn't kill you. It's what you exhale. What it does when you're measuring CO2 is indicate the level of ventilation. So it's a good variable to measure to see how much mixing, how many people are there, what's all going on, what's the need. So what's going on now is we can take a large room like this right here, we can put CO2 monitors in there, and then we can control the ventilation on that. In this little room right here, we had a big chill water plant serving this whole building. It's going to make 1% difference. It's going to be a little drop in the bucket. But if we had 20 of these rooms or 30 of these rooms, or if we're in a school building and it's the auditorium, the gymnasium, okay, and the cafeteria, oh my goodness. Turns out those were half the load. And you had them cranking away all afternoon long with no one even in there. So that's when it really starts to make sense to think about, let's only ventilate when we need to, because this chill water plant is driving hard to serve a load that isn't even there. So demand-controlled ventilation is a really good strategy. Very low cost for the benefit. Very low cost. And the CO2 monitoring systems are getting more and more reliable, sophisticated. As long as you do calibration on a regular basis, you've got an actual system maintaining. And this, from a safety point of view, makes more sense because you're actively controlling it. You're not just saying, like Tom said, 100 square feet per person. You're guessing. This is an actual way to control ventilation. Now we're getting into younger Tom's world. Don't assume that since there's a whole system, building automation system working, that it's calibrated. There's a good one right there. 15 years into it, how often have you calibrated all these sensors? I did a job one time for Social Security Administration around the country, and typically these buildings are housing thousands of people. These air handling units are several 100,000 CFM on the penthouse, these GSA buildings. 1 degree between 55 and 56 was a massive amount of electricity just because the sensor's out of calibration. They never even thought about it. So just calibrating, recommissioning, getting everything back to what it's supposed to be can make a dramatic improvement sometimes in buildings and help the chill water system.
Every year, standards change and room requirements change. And I think that when you check the rules, you call, you actually modify there.
Yeah. I was actually talking about outside air, then I started talking about just regular supply air. But your point is, maybe you come upon a building as an energy engineer that turns out you actually need more ventilation than they're bringing in. I've been there many times. Yeah, you're just going to have to go to the owner. Yeah, you're right. That's when an energy efficient solution like demand control ventilation, turns out, sir, Mr. Owner, you don't even have enough ventilation in here. I'll tell you what though, we're going to increase the capacity of the system and get it there, and then put this in there, and in the ultimate end of it, we're going to be close on your energy bill because we're going to bring some efficiencies. Maybe we're going to have to look at heat recovery wheels. Tom's talking about a laboratory where they have to bring in tons of ventilation for fume hoods. Well, they're putting heat recovery in there. So that could be a great opportunity to mitigate the, quote, damage, getting them up to code. You're right. And that has happened many times to me. You're absolutely right. Okay. So any questions so far? Any comments? Anybody have something they've been wondering about? A case study? Okay, keep thinking. Okay, now let's talk about the chillers themselves, because what we've been going down through in the first two were, could they be turned off, could they be turned on, could other stuff get changed to help them? We didn't even do anything with the chillers at all. And again, when you're applying your energy engineering mind to any system, boilers, chillers, windows, roofs, again, same kind of process should occur. Start thinking about the environment. Can it be turned off? Can it be turned on? What is going on? What is the load? Can you change your strategy before you start attacking the piece of equipment itself? So loss of refrigerant. When is when is R123 going to be banned by the Montreal Kyoto Protocol? What year? 99.9% reduction. 2013? 30? It was, but now it's 2020. So 2015, the protocol is calling for 95% reduction. So next year, we should only have 5% of the 123 that we had before and the 22. So refrigerant, oh my goodness. That stuff gets expensive. When you start not producing it, the price of it goes up per pound. Anyway, when you're looking at a chill water system or chillers or rooftop units or refrigeration, if there's an evaluation going on, you're the engineer there, man, you should be asking the question, hey, is the refrigerant at the right level on all this piece of equipment? Did anybody check that? You'll be the smartest person in the room because, believe it or not, that can be the source of an abundance of problems. Okay, this basically goes down to a scenario where what we found out was there were refrigerant losses and it wasn't being monitored and it wasn't being taken care of. It has a huge impact to the owner's, wallet, production loss, et cetera, et cetera. So knowing that you have the right amount of refrigerant, monitoring it is very, very important. In a chiller, packaged equipment, the oil is in with the refrigerant. It's a mixture, and it's a can. So this really isn't anything you can do anything about. But in chill water systems, larger chill water systems, the oil is a separate system. And let's just say oil temperature and oil flow and everything like that has to be looked at very carefully. If you're in PNC Bank building or PPG Tower or Oxford, any of these big buildings downtown have chillers, got to make sure the oil system is absolutely correct. That was another thing we did in this case. And it, again, has a direct impact on the efficiency of the system and can cause dramatic shutdowns and problems. So refrigerant, oil. Can the efficiency be improved through simple retrofits? Okay, we've gone through our procedure, done all the hard work. Now we're getting down to the typical place that some engineers, some energy engineers start. Well, they shouldn't start here, but if they've done the first 3 steps, then you got here. Okay, it's time to start looking at retrofits. Okay, everybody knows about variable speed drives now. 10, 20 years ago, it was like this newfangled idea. At this point in time, everybody understands there's many companies out there that have them. The electric companies offer rebates. Act 129 in Pennsylvania, it's one of the things that you can get money for your customer. I just caution, some people have gotten into the thing now where they're just throwing VFDs on everything, mindlessly, just to get the rebate, just to say everything is variable speed. I'm a little bit more old school than that. I mean, I think you need to be really careful. Listen, we talked about cooling tower. For this system, Mr. Owner, it's better to let your cooling tower stay on because the overall efficiency of your chill water plant is improved on an annual basis by just running the towers as cold as they possibly can. So we're not going to put variable speed drives on the condenser pumps. Oh, okay. But we are going to put it on your chiller because it can make a dramatic improvement in efficiency. The chiller is now rendered oversized. We love your engineer. He did a great job 10 years ago. But you've done window and lighting retrofits. Your people have become more efficient. Some are working at home now. Your cubicles are way more efficient. And your load is 70% of what it was when these chillers were put in. By putting the VSDs on there, the chiller's only running between 40 and 60% anyway. It's now going to operate extremely efficiently because with the VFD, the chiller is going to be a smaller chiller in real life during typical operation. However, its evaporator and condenser barrels are as big as its big brother. So it's going to be a super duper efficient chiller now. No one will buy a chiller with half the chill water capacity and double the heat transfer capacity. It'd be a dumb idea. It would be the chiller that didn't get bought because it'd be too expensive. So let's make lemonade out of lemons and make your chiller smaller because your load is smaller. Now, there's still that July day when in Pittsburgh dramatically it goes up to 100 degrees. It's still there. The next one that probably makes sense is the chill water pumps. They run flat out 3,000-4,000 hours a year regardless of the load. Nighttime, weekends, you can't turn it off. Okay, you got to keep that chill water system going. And again, this could apply to heating water as well. Let's look at two-way valves throughout the system in the air handling units or your loads or let's just say you have a stamping plant or pultrusion or whatever you've got, whatever the loads of chill water, hot water, let's go ahead and let that system go down to whatever's needed. We'll put a variable speed drive on the pumps. Those make a ton of sense, okay? I wouldn't go crazy with variable speed drives on every little motor in the building, but those two that I just mentioned, very, very strong. I just show this just to show that from our point of view, York, Johnson owns York. We've been through the whole thing. I mean, this thing is embedded into society now. This is not a new idea. You come upon a system and you've been through all those, can you turn it off? Been through all of this discipline, and you're still surviving in your energy engineering. You haven't already solved the world's problems with the first 3 questions. You're down to it. Okay, fine, I give up. You might need to start looking at retrofitting the system to variable air volume. Why did I have that like pessimism and stuff? Well, this payback is going to be way long. This is going to be difficult. And it may seem simple on paper, but trust me, I've been through this a lot. This you need an architect for, because this is going to get into ceilings, this is going to get into zones, this is going to get into all kind of stuff. And this usually is best done as an entire retrofit or a large-scale renovation of the building itself. I've many times told an owner, he's like, I want to convert everything to VAV. After 6 months, I'm convincing him, look, it makes sense not to do that. Let's wait for 3 years when it's time to completely overhaul the building and do it as part of that. However, in a single case or in a certain situation that lends itself to it, maybe it could be done. VAV is not going to take away the biggest load on the chill water, because VAV is not going to reduce the maximum load. If it's going to be 1,000 tons in July, it's still going to be 1,000 tons in July. The variable air volume system is going to save you on fan horsepower during the spring and fall. That's what it's going to do. And hopefully improve your space temperature control. So there could be some definite benefits, something that may make sense in certain situations. Okay, we've been through all that. Now we're down to heat recovery. Okay, what is the efficiency of power production in the United States? For every BTU in, how many BTUs of electricity do I get out? 30%? What'd you say? It does, but I'm just saying just generally. He's really, really close to right. It's like 1 to 3. It's 1 to 2. In other words, for every 3 units in, you get 1 electrical out with gas, with oil, with just traditional power production systems. I mean, hydro obviously is different, nuclear is different, but I'm talking about just traditional, you're just making power, okay? It's roughly 33%, okay? The power plants you see that are burning fossil fuels. So when you're doing that, like I said, you're putting 3 units in, you get 1 unit out. What is the efficiency of cogeneration? $70? Yep. 70, 75, 80%. Yep. Why? Cogeneration takes advantage of the heat that's produced during power production, uses it for something, more power, cooling, heat, something, and the overall efficiency of the thing is 80%. And some people think out there, and they're probably right, that cogeneration is like the answer. But it's not always possible. I mean, you don't always have something to use that heat on. You don't always have a load large enough that reintroducing the heat to make more power is even possible. It's just very unwieldy. Okay, so cogeneration, oh man, I wanted to put a cogen plant in that, but it never could get approved. Okay, what's the little brother of cogeneration? Heat recovery is really the same. I mean, when you're doing something, you're making chill water, you're throwing heat out the cooling tower, it's bad. If you can use that heat, you're cogenerating. Now, don't say you're cogenerating because the cogen people will be mad at you, but you really are. You're using one fuel source to make chill water and something else through that heat recovery. So we've got cogeneration in the form of its baby brother, heat recovery, in cities all over the United States. That will be a great, I've done a couple of these things. The CO2 reduction is phenomenal because we all know when you're taking green tags on lighting, VSDs, it's from electricity, right? What is the amount of kilograms of CO2 per kilowatt in Duquesne light? Okay, I'm not asking for the answer, but it's something. It's based on nuclear, water, hydro, gas, something, okay? Well, when you shut off a boiler on your site, that's way more CO2 reduction than what credit you're taking for the power company's share. Do you understand what I'm trying to say? So even though heat recovery, people say, oh, the payback is 7 years. No, wait a minute. CO2 reduction, you're trying to be green. You're trying to be, you know, sustainable 1,000. You want to try to get rid of thousands of tons of CO2 per year as an organization. Heat recovery, believe it or not, shutting off a boiler in your site dramatically improved that process. So what we have, there are chillers out there that actually don't reject the heat to the cooling tower. They work in reverse. They actually make heat and reject cooling to the cooling loop. Okay? I mean, if you take a chiller, for example, a screw chiller, it has a fixed orifice, standard software, controls leaving water temperature, it's not compatible with a variable orifice, blah, blah, blah. You switch it around, make it a heat pump, make it actually make hot water. Variable orifice, unified screw software, controls leaving condenser water temperature. Condenser water is the heating water. See? Think about it. Remember we talked about the evaporator, that's chill water, condenser, cooling tower water? Well, when you reverse it, the condenser water is now the favorite. It's the one making the hot water that you care about. Got to put insulation on it now, and you got to like worry about it and control it on that. And then the chill water is the benefit. Okay? Heat recovery as opposed to a heat pump. They have those too. They're possible. You have a chiller that's chugging along and you have something like domestic hot water or a process. You can do heat recovery. Heat recovery takes no change to the chiller. You just grab heat off the condenser loop, and instead of going to the cooling tower, low-grade heat now, remember, because cooling tower temperatures are low. You can maybe use that. That's great. But a heat pump is a whole other story. A heat pump is different. It's actually driving the control on the hot water side. And through the right changes in the machine, you can elevate that temperature. Instead of 100, instead of 95, it could be 105, 125, 130, all the way up to 180 degrees. In the Arabian desert, we use chillers that condense at 168. Why? Because there's no water. They've got no cooling towers. So we use radiators in the desert to drive the heat off the chill water system for the airports, like Abu Dhabi, stuff like that. So in other words, chillers can be made at higher refrigerant levels to reject heat at a much higher temperature, right? Well, the reverse in a heat pump can be also true. That you can make a heat pump to make 140 degree water, 150 degree water. Why would you want that kind of temperature? What would you use 150 degree water for in a building around here? What would you do with it? Any ideas? Space heat. If you had chill water load in the wintertime, let's say you had a bunch of surgical suites that needed cooling even in the winter, that'd be good. What else could you need 150 degree water for during the summer? What's that? Yeah, you need 140 degrees to make domestic hot water. So if you had a huge dining room or cafeteria with massive dishwashing, what about like a surgical suite, a laboratory, a library, a museum, anything that needs what? Control. Not only temperature, but, thank you. So where we see these machines is in places that have reheat. Reheat is the bane of all energy engineers. We hate that. I mean, why are you making reheat in the summertime? That's crazy. Well, there's no other way to control humidity, and we're not going to put desiccant you know, low humidity systems in because it's only 45 to 55 that we want to maintain, okay? Oh, it's painful drawing the reheat systems on the paper when you're an engineer because, man, think about the simultaneous heating and cooling. Well, okay, look at that. Making temperature for cooling, making temperature for reheat on the same machine, no cooling tower. Perfect solution. Little known, but, and we have the machines, York has the machines all over the place. Carrier makes them as well, and they're all over the place. It's just that it's not really a well-known thing, but think about it. It's a great solution. Finally, okay, I give up. The chill water system, we went through every one of those questions, and it couldn't come up with a solution for any of the, we couldn't do anything, or we did do something, and we want more results. Now we're talking about retrofits, okay? When you're talking to a chiller salesman like myself, okay, this is where they start. Okay, I got here after 45 minutes, after we did all our diligence and our homework and our painful procedures, okay? We're finally here, okay? We've earned the right to talk about a retrofit, okay? I'm not going to talk about all kinds of chillers. I'm just going to talk about something interesting for you. Did you know that now there's several manufacturers, York being one of them, that makes a chiller that has a magnetic bearing on the compressor? Did you know that? You're smart. Okay. So there's no oil in it. We got rid of that one fluid that was a pain in our, that we have to keep maintaining the oil pressure and oil temperature and all that kind of stuff. We got rid of that whole thing. So now it's magnetic bearing, oil-free. Okay? York called it the YMC squared, goes up to 640 tons. I mean, we make it in a tonnage that fits buildings like this. So efficiency is higher, 10%, typically. Depends on the load, depends on the situation. Life is much, much longer. It's quiet, variable speed drive, oil-free, magnetic bearing chiller. It's even more efficient than our normal variable speed drive chiller. So, what do you think the kW per ton of a chiller should be, like if you spec'd it out? Like, let's make a engineering spec. It's a tough question for this crowd because a lot of you aren't really in that business. But let's just, I'll call on Jet. You just thought, well, what should be a kilowatts per ton of refrigeration? Typically used in a spec. 1.8. Yeah. Yeah, most engineers are going to be like anywhere from like 0.7 to 1, depending on the system, somewhere in there, depending on what equipment that they're hopefully is going to be provided as proposals. They're trying to get something like, okay, this guy is operating. This is the hottest day of the year. Remember we talked about the cooling towers? This red line is the hottest day of the year. Okay, that's when your cooling tower is making its design temperature. That's it. Many, many, many other days of the year in Pittsburgh, it can make 75, 65, and 50. It can make the cooling tower that was designed for the worst day of the year, okay, sitting out there on your building in Pittsburgh, can do much better than that on a typical day. So let's just call it right in here. And where do you think a typical chiller runs? Like what percent do you think it typically runs on average? Right. 60 to 70%. That's like any system. I mean, anything that's designed runs. And I've seen much lower in real life, by the way, just from my travels. Oh, it runs at about 70 or 80%. We do data logging, it's 40%. I mean, so let's just call it 60, 70. So we're in here, and we're in here. So look at this. Look where my finger is coming out in kW per ton. I mean, 0.3, 0.4. That's half what a typical chiller. So, good news. The thing that uses 40% of a building's electricity, the chill water system, is now getting more and more efficient. So, but remember, we went through the discipline of proving that a time for a retrofit was now. We needed to go through all those other steps. It's got a magnet, state of the art. We're not the only ones who make it, but you could spec it now and get several responses for a magnetic drive chiller. It would be the right specification in a building today, in my book, for efficiency and for long life, for quiet operation. Say you had a 300 or 400 ton chiller you needed in a new building, you could get 3 or 4 companies to go ahead. See, great question. Is it more expensive? Let's say the price is more expensive. Is it more expensive over the? Sure, the first cost is more, but who out there buys like the base model GM car here? I mean, you know that a better value is over the life. The energy efficiency, the operation, the aesthetics, everything involved in this thing, I mean, is going to make it a lower cost. Several times my team has been assigned to kind of defend our proposal. A customer said, make a third-party cash flow life cycle analysis of this. Always does this come out far better. When you look at the maintenance, and our service department will put their money where their mouth is. Our service department will quote a lower number for this guy than a machine with oil in it. That's just not like talk. So these are details. We're starting to wrap up. These are some tidbits. Any questions? Or I thought for your knowledge, you'd know. Does anyone know or have heard of modular central plants these days? This is something we're doing and other companies are doing now. Sometimes when you have a building, you want a highly efficient system. There's no floor space. We can make a modular chiller plant, set it out on the parking lot. It's not a building, Tom. It's a piece of equipment on a pad, so it doesn't involve all the plan sets, the reviews, and is a really good way to address an efficient upgrade. You can put anything in a module and make it highly efficient, built in the factory. We also can put variable speed drives in air-cooled chillers today. I don't know if you guys knew that. The sort of baby cousin of a chiller is an air-cooled chiller. It doesn't have a cooling tower. Still make it chill water, but it's up on the roof or out in the parking lot. It doesn't have condenser water. It doesn't have a cooling tower. These things traditionally were 1.5 kW per ton. So they were pretty inefficient. Okay, they're driving these down below 1 kW per ton with variable speed drive technology. So that starts to make sense in certain situations where you really just don't have the money or the space to go for a full chill water system, but you want efficiency. We have one, yep. We take one of our variable speed drive air-cooled chillers to another factory and then put a water coil into it. If I think what you're saying is so then in the wintertime it's direct, it doesn't use refrigeration, it actually just is essentially a fluid cooler, a closed circuit fluid cooler. It can operate with its fan and give you that chill water in the winter with no refrigeration load. Well, it's not evaporative, but the point is, if you're comparing it, if you're looking at, okay, in order for me to get evaporative cooling in the shoulder months with a plate frame heat exchanger or with like a free cooling cycle, okay, I've got to spend the money on a cooling tower, okay, and I'm going to have a traditional chill water system. What our option does is says, okay, you're down to the air-cooled size, 200 or 300 tons, but oh man, I don't really want to run that in the wintertime. Are you kidding me? Surgical suites, something that still needs cooling. I don't want to run a chiller in the dead of winter. So the option that we have is we'll put just a simple radiator in that thing. So it'll actually provide that chill water in the winter just on the dry, just on the sensible. It doesn't have the evaporative effect. Now, there's some equipment made in Europe that I've put on some plants here in the United States that do that. Frigel makes it. I've used it. It's actual evaporative and dry in the same machine. But again, we don't make that product, but that product is out there. You can spec that. It's expensive, but it pays back because, as you say, that stretches the window of free cooling out into September, October, and March and April because of the evaporative before you need mechanical cooling. Was that what you were talking about? Okay. Yeah. Yeah. Depending on the load, depending on the hours of operation, you're absolutely right. It'd be like A, B, C.